Any questions from last week? Have you guys been able to follow through on the lectures after I've posted them?
All good on my end.
Okay.
Yeah. I wondered if we were going to maybe get a study guide for the first test, or should we review the lectures and look at the end where you you list like the most important
Key
things?
terms.
Yeah.
Yeah, so there's probably not going to be a review guide. The best way to go about studying will be reviewing the quizzes we've had thus far and the lectures. So those would be the two biggest pieces. Know that you will need to do some calculations as part of it. Like today, we're going to cover z-scores. That's something you're going to need to know how to calculate. And then it might be helpful actually for me to just pull this up real quick because the exam is coming up on October 14. We still have some time. So we're going to be discussing, today we're going to talk about z-scores and the normal distribution specifically. Then we'll move into just general sampling. And then the, sample size in terms of one-tailed versus two-tailed test, what that looks like, and then it'll be the exam. So we've got a couple more lectures before the exam is set.
Okay.
So we'll, go ahead.
Oh, sorry. I was just gonna say real quick that, so should we be prepared to just be familiar with, like, for example, the like standard deviation? I know how to do that, but I had to like, for like the lab, for example, but I had to refer back to the lecture. Is that something that I'm gonna have to like memorize?
No, and the reason why is because the exam is going to be online. So we'll get it started at 2 o'clock like we do any other class. I'll make sure that my cell phone number is on the top of the exam and you guys will start taking it. Now, because I can't monitor, resources that are utilized, that would be made available to you guys. But, if we were doing an in-class exam, I would still allow like a 3x5 card of formulas. This class is not about testing your memory. That's not the job of it. It's knowing how to manipulate the data and how to make sense of it. Yeah.
Okay.
I mean, you should review it so that when the question's asking, you're not like starting from ground zero and then having to like look it all up. It's still going to be a time limited exam. It'll need to be submitted by the end of our regular class time. So if you're spending an hour figuring out each question, you're going to time out. So reviewing ahead of time is going to be important. Make sense? Okay. Any other questions? Was the lab, was that okay?
I thought it was pretty straightforward.
Kind of a straight replication from what we practice in class. So hopefully that wasn't too complicated. Okay, well then let's dive right in and let me find my screen here. Okay. I always hate when the big bar's up there. There we go. Let's make it go. Okay, I realized that when I move our faces and all that, it literally records my screen. So when I go back and upload it, you guys can see me like moving our faces and moving them back. And sorry if that's distracting. That's not the goal. It's just half the time our faces are in the way of the slide. So, okay, so today we're going to be talking about the normal distribution. Now we've talked about the normal curve, right? That looked more like something like this, right? Like a normal bell curve. So here, let me do this so we can see what it looks like, right? That's a normal curve. Now we're going to talk specifically about a normal distribution. The main goals we have for today is to explain why it's important that we use a normal distribution statistic, specifically when we talk about a bell curve. And then the bulk of the class today will be discussing how to transform a raw score into a z-score, and obviously vice versa, so you know how to manipulate the formula by flipping it on its head. And then the reason why we use z-scores compared to just raw scores. So that's big picture what we're trying to get at. Okay, So normal distribution, as I just showed you on my little doodle, it's bell-shaped, right? It's a normal curve. It is symmetrical, meaning if you cut it right in the middle of the mean, half of it is above, half of it is below. And the mean, median, and mode, with a normal distribution, they all coincide right in the middle, right? They are all lined up. Now, we've talked about in the past, mean, median, and mode are not always all lined up. Depending on the type of distribution you have, it's quite possible that they vary, right? Like if you have a skewed distribution, that's more, I should have just a whiteboard all the time handy, right? So if you have a distribution that's like this, right? That's gonna have a different mean, median, and mode than the normal distribution that I showed you guys earlier, at which point it's all right here down at the middle. Okay. So why do we talk about this? So it's important to recognize that in the everyday world, in the natural occurring situation, a normal distribution is kind of rare, right? Like it's how the more people you include in your sample, the closer it'll come to a normal distribution, right? Because it tends to behave more normally. But for it to fall like this, we really talk about it being more of a theoretical ideal. It's often not based on specific data because data doesn't behave in an ideal world, right? There's always going to be an outlier. Like for instance, I could say that on average, right? And I'm making this up here, so feel free to correct me, but let's say I'm looking at the average height of men in the US. It might be 5'10", I don't know, 6? 5'10" seems kind of right. With some people obviously being taller, some people being shorter. Now, if I flip this on its head and I said, well, now what is the average population of a man in Grand Rapids? What do we think that would be? I think there would be a skew because there's a large Dutch representation in Grand Rapids, and usually folks from the Netherlands tend to be taller, just in general, right? The same way that if I said, well, what about in Southern California by San Diego, where maybe there's a larger population of folks from Latin America and those averages are smaller, right? So obviously the overall average for the entire country is gonna gravitate towards the mean, towards a middle point, but there's gonna be variation based on your sample. So it's important to recognize that our normal distribution is really just an ideal. It's not always 100% correct or representative of what you actually see in the real world. So it, again, doesn't match it perfectly. All we can do is approximate it and speak to it in relation to the normal distribution. So again, a normal distribution is symmetrical. You can split it down the middle and it has equal sides on either end. It is unimodal, meaning it only has one peak or one mode. We talked about bimodal distribution. That's when there's two separate peaks. So if a test exam, for instance, tons of people got A's, tons of people got C's, that would be a bimodal distribution that showed that either people knew the information or they didn't know it at all. And again, based on the unimodal distribution, right? So most scores fall near the center and fewer are at the tails or at the extremes. And it looks something like this. So again, it all meets down the middle during mean, median, and mode, fewer here at the tails. That's your normal distribution or normal curve. Okay, let's talk about some nomenclature here or some language so we all are talking about the same thing. So this here is in terms of population. Remember, what is an example of a population statistic that we have? Do we often poll an entire population?
Not often, but the census would be a population.
Perfect. Whereas a sample would be what?
How many people live in Grand Rapids?
Exactly, some sort of subset. So the goal of a sample is it's a smaller group that's more easily attainable that can represent the larger group in some fashion. Okay, so these are the values. You will need to know this. Okay, so in your text, they talk about this as well. If you're looking at the mean of an entire population, this is the nomenclature for it. It's called mu. So it's like a U with the longer tail at the front. If you're doing a mean for a sample, you would do a large M, or you might also see it like this. I think your text occasionally will do this too. So, oh heavens, sorry, this is not very clear. My little doodle is going to get even smaller. You guys see that? It's like an X bar. That is mean. So when we were practicing last week and we were taking X minus the mean to get to the standard deviation, the mean was notated with an X and a bar on top. It can also be notated with a capital M that's italicized. A standard deviation for a population is a sigma. So again, it's like a circle with an extra tail. Whereas for a sample, it'll just be SD, standard deviation. Sometimes you might see it as a lowercase s as well. And then the variance, as we figured out last week, the variance is whatever the standard deviation is squared. So sigma squared or SD squared or S squared. Those will all be the nomenclature for variance. Okay, now we talked about this last week as well. So in a normal distribution, again, based on this normal curve, scores really behave the same no matter what it is you're measuring. So around the mean, if you go one standard deviation to either side and you were to make a line through it, just like it is right here, you can see this is 34.13% of the population will be there, or the sample in there. And on the other side, 34%. So if you're looking at the scores that are within one standard deviation of the mean, up plus or minus, you're looking at 68.26% of the population are there. Now, if you go one more standard deviation, you're adding another 13.6% on either side. So then for a total of 95.46. So again, if you're thinking about IQ scores, we talked about this in the past, and we know that an IQ score lies right at 100, standard deviation of 15. If someone scores 128, they're within 2 standard deviations above the mean, which means 95% of people, like they are like part of the 95 percentile that has a score right there. What we're going to learn how to do today is specifically finding that score, 126, and figuring out what is that percentile. Like if I put a dot right here, what does that tell me about that score in comparison to the rest? Because this is helpful in showing how many people fall within that range. Conversely, right, if you know that 95% of people fall within 2 standard deviation and you get a score that's 2.5 standard deviation, you can figure out that that's less than 5% fall here. In fact, it's half of that, right? Because 5% divided by 2 sides is 2.5. So they'd be right here. So this is what you guys need to start getting familiar with. The reason why we use a normal distribution is because it behaves the same way all of the time, right? It is an ideal, but we end up taking our scores and we convert them to this ideal so we can start comparing different things and having it make more sense. Okay. This is, again, just what I described, just with simpler terms. So your mean right here, if I compare it to a z-score, and we'll talk about that in just a second, that would be a z-score of 0. So when you're doing a z distribution, the mean is 0, the standard deviation is 1. So as you can see, within 1 standard deviation of the mean, that's 68% of your population. You go another 1 standard deviation this way, you're adding an additional 28%, right? So you get to that 95. Okay. This always remains. For a z distribution, this is what it looks like. Questions about this thus far? So far, so good?
So far, so good.
Okay, or maybe we've got a, I don't know, but I don't know what question to ask. Let's keep going. All right, so how do we describe a score? So knowing one score tells us very little about how it relates to a whole distribution of score. Let me give you an example. You have a friend who just had a baby, right? Baby is 6 months old, and they tell you he is 23 inches. Do you act surprised, or are you like, whoa, giant, or whoa, your baby's super little? What does 23 inches mean to you in terms of their length?
Currently nothing, because I don't
Nothing. Well, that's why I picked that example. Maybe for some of you guys who have younger siblings, or maybe you have children of your own, or nieces or nephews. Does anybody like knee-jerk reaction? You're like, oh, I would know how to respond to that.
That's a big baby.
What's that?
That's a big baby.
That's a big baby, right? Or if 6 months old, maybe that's a little, right? It all depends. But it gives us zero context, right? To just have one value in the absence of how it relates to everything else means very little, right? The same could be said about IQ, right? If somebody just threw in, and you hear that all the time, people are like, oh, Einstein was so smart. His IQ was insert whatever absurd number, 500. No, it doesn't go that high, right? But you put some sort of number, right? And you're thinking that's high, right? But anyway, that's a sidebar. I just had this discussion with my children. No, his IQ was 1,000. I'm like, oh my goodness, I have failed you as a parent. Okay, so comparing a score to the mean of that distribution will show you whether it is above average or below average. And that's what's meaningful. So you know how to interpret it. Like, how does that make sense? So this is why we do what we do. We figure out the mean, we figure out the standard deviation, and then to be able to compare two different sets of scores and know how it relates, we put them on what's called a standardized scale, which is what the Z-score is. So we'll talk about that in just a second. So how do we relate a specific score to the mean? That's partially what we did last week, right? So we figure out the mean, we figure out that score, and we figure out where it lies in terms of how much it varies away from the mean, or what is the standard deviation. It's talking about the spread, again, of our distribution and the spread of the scores. So here's an example. So in this here, one student, here's a score in relation to the overall sample, right? Here's your mean. This shows you it's one standard deviation, and here's a score. So it's the measure to this particular example in your text, the measure to the extent of which students are morning people. So most people are right around this. Again, this is a terrible example because we don't really have a whole lot of context as to what it means. But if this is the average, he is greater than average in terms of being a morning person. Okay. So a Z-score talks about the number of standard deviations that a given score is above or below the mean of a distribution. Now, again, it can be used to standardize any type of raw score. Miles, seconds, length, percentage correct, pounds, really any measurement you can think of, we can plug it in on a line and figure it out. And it shows where the score is then located on a normal distribution. So again, if this is my mean, and this is back from this slide, right? The mean is 3.40. So this is the mean. Again, a Z-score always has a mean of 0. So you anchor it is what you do. This is my mean is 0. Then you figure out what one standard deviation below or above the mean looks like. And it's utilizing just a score of 1. So in a Z distribution, a standard deviation is always 1 point. So first one, here's +1, then +2, obviously vice versa. Okay. Now here's the number of times each hour that two children spoke, shown as raw scores and Z-scores. So this is the times spoken per hour, right? The mean is 12. And I know this because the Z-score is 0. And Jacob spoke 8 times. So I can see that's exactly one standard deviation below the mean. Whereas Ryan, who's a chatterbox, spoke 20 times. That's 2 standard deviations above the mean. Okay? Questions about this so far? Z-scores kind of conceptually making sense, anchored at the mean, Z is 0. Standard deviations, instead of taking on weird numbers with decimal, it's always going to be 1, 2, 3. They move up by 1.
Yep.
Okay. All right. So here's how we calculate a standard Z-score. So to get Z, you're going to take your individual score minus the mean divided by the standard deviation, okay? Again, this is another way that it's written in your text. It's the score minus the mean divided by the standard deviation. Now, if you want to figure out a raw score, you have a z-score, but you don't know the raw score, you would just, we just manipulated this exact formula. And so a raw score would be your z-score times the standard deviation plus the mean, okay? Good to know both of those. We're gonna do a lot of those calculations. You don't need to memorize it, you just need to have access to them. Okay, so this is an example. Here's my sample size, very significant, over 1.1 million. And there's the three different sections of the SAT scores. And you can see here the mean and standard deviation for each, right? So the mean for critical reading, for instance, 485 with a standard deviation of 110. Again, mean of the math one is 501 with 117 as the standard deviation, and writing is 475, standard deviation of 109. Now, if I specifically want to know what is the z-score for a given score, right? It's not written on here, but let's say a hypothetical one is 584. We would take 584 minus the mean, and here it is. This is the one we're doing for critical reading. I think that's, or was it the other one? No, it was this one, writing. Sorry about that. So the mean was 475, standard deviation of 109. So then I do 584, which is the student's score, because now we're trying to figure out, like, is 584 a good score? Let's figure it out. Minus the mean, which is 475, divided by the standard deviation, which is 109, which gives me here a z-score of 1. Or it's exactly 1 standard deviation above the mean. If somebody had an SAT score, for instance, of 366, you take that minus 475, you get negative 109, gives you a z-score of negative 1, which is exactly 1 standard deviation below the mean. Okay, the above and below the mean should make sense because of the score that you're evaluating. If it's above the mean, right, 584 is greater than 475, already you know that this is a score that is above, it's better than the mean. But as to know where it lies in relation to everybody else, that's when you get your z-score to be better able to evaluate its exact location on that line, okay? All right. Very similar again. So here's the raw scores. You can see 475 is a z-score of 0, right? Because that's the mean. And I know that the standard deviation is 109. So up 109 is 584 or plus 1 z-score. Then you go up plus 2 z-score and so on. And here's how it fits again on our normal distribution, where 68% of the population falls between 1 standard deviation of the mean. So plus or minus 1 z-score. Okay, this is just all bringing it together. So we've got normal distribution, normal curve, and now z-scores. So 3 things you need to know about z-scores. The sum of the z-score is always going to be 0 because the mean is set at 0, right? So much like when we added up our column there last week, doing x minus the mean, right? You're taking it away from the mean, so whether you go above or below, it's all going to come right back to the mean. So the sum and the average of deviation scores, again, must be 0. So it all falls back on that mean or 0 point. The standard deviation of a set of z-scores is always 1 because the deviation scores have been divided by the standard deviation. Okay, this is an important point. This is how we simplify everything with z-scores, so that instead of having a standard deviation of 22.7983, right, we make them easy whole numbers. It's going to be 1, 2, or 3, all whole numbers with a change of 1. We have a lot of deer in our backyard and our dog's going crazy. Sorry about that. And then z-scores follow the same distribution pattern as the original raw score. So if the original distribution was skewed, your z-score distribution will be skewed also. It'll mirror it. If z-scores are standardized, or they are standardized, I should say, but sometimes they're called standard score when they follow a normal distribution, okay? And it's represented by z-scores, the normal distribution is, then it's called the standard normal distribution. This is just stuff about nomenclature. You don't need to worry yourself as much about it, but just some of the properties of z-scores as a whole. Okay. Now, how many of you guys own the textbook?
Yes.
Yes. In the appendix, you are going to find, and in fact, let me just show it right here. It shows that it's table 3.1. If you do not own the text, don't worry. You can find a list of z-scores anywhere online because they don't really change, right? So, but this will be very handy, and for the exam, you will need to have it. The idea is if you plug in a z-score, right, somewhere along those lines, it'll tell you exactly what percentage is under the tail. So for instance, here, if you got a score somewhere here, so that shows for a positive score, something that's above the mean, it would be able to tell you what percentage of the mean to z. So if I know below the mean, what's the percentage here that's comprised of the mean and below? How much of the population lies in this section that's white?
50%.
I didn't hear, sorry.
50?
50, absolutely, right? So I'm at, again, a normal distribution, normal curve, I split it in half, half are below, half are above. So I know that this section is 50%. So if I grab another point somewhere here above the mean, right, I'm gonna get the percentage of this section, which I then add to my 50%, and then I know exactly where that score falls. It's the same idea as again with the percentile, right? It'll give you a point. Okay, now if it's really far here in the tails, I can also calculate it this way, right? So it'll either give me this section that's from the mean to z or the percentage that's in the tail, okay? And then the same will be true on the flip side. Okay, let's see here that I want to say something else about that now. Okay, so if a student, for instance, has a z-score of 0.64, what percentage is between the mean and the z-score? It would be 23.89%, right? So again, a z-score of 0.64 is positive, z-score of 0 is the mean, 0.64 is above. It's almost a standard deviation above, because what is one standard deviation in terms of z-score?
+1. Right?
+1, right? So 0.64 is approaching 1, right? So that would be 23.89% that is above the mean, okay? Same thing. If a student z-score, when we know that 30% of students scored higher than her, so now we're using it, kind of flipping it, okay? So if I know that 30% of students scored higher than this particular student, what is likely to be her z-score? I would go right here to the 30%, right in here, right? 30% scored higher, and I could figure out the z-score is 0.52. In the examples that I will give you guys on the exam, it's going to be far more specific, because I always get students who are like, well, there's 3 scores with 30. What is it? This would be the highest level. Anyway, it'll be more specific than that. But this is to give you an example of how you can manipulate the numbers to answer your specific question. And this is all based on the table that's in your textbook. Questions about that? It's a lot of new material. Maybe it's not new. Maybe you guys have covered z-score in a class before. Okay.
I'm good on my end.
Not on your end? Okay. Well, let's
I
yeah.
just want to say I have the 9th edition and I can't find it at all, like that table.
You don't have an appendix in your text?
Or like I do, but I can't find that table.
It should be table A1.
Okay.
So it's in your appendix, and you're gonna see like a super long list of numbers like that, like this obviously truncated and it's only showing a tiny bit. and it'll run through all of the z-score possibilities with the percent at mean to z, and then mean z, percent and then tail. Okay. If you can't, again, if you don't have it or can't find it, know that I'll attach a Z sheet to the exam because they're readily available online, because those numbers, they don't change, right? It's just z-score is a z-score.
Can you find, like, in the last example, how many people scored below her? Or can you not do that with this table?
I love your question. Absolutely. And so here's the way we would do it. So it's just flipping it, right? So if I know that 30% scored higher than her, I could do 100, right? Minus this 30, and that's how I would know. This whole section here would be 70 whatever percent.
Okay.
Does that make sense?
Yeah, it does.
Okay.
I have a question.
Yeah, go ahead, Jenna.
So, does this, I mean, I know you just said you can see how many scored below, but does this table not show, like, the left side of the distribution then?
So great question too. So because all of the numbers, right, standard deviation of 1, whether it's +1 or -1, the numbers are just going to be exact reverse. So usually in the appendix of textbooks, and I've used 3 different stats textbooks, it only shows to the right of the mean.
Okay, so it's
Because you can take the data and just do 100 minus, you know.
got it. Okay.
Yeah. Does that answer your question?
Yeah, thank you.
Okay, no problem. Okay, great questions. Okay, so again, how do we transform z-scores into specific scores, right? So I know, this is part of what I was discussing earlier. If I know the mean is right here, I know that this area in white of our curve is going to be half of the total area, or 50% of the scores live in this section. So when I get a positive z-score, I know that it's going to be the mean or above, right? Because the mean is 0. So if the number is positive, that's going to be a greater than the mean score. If I get a negative z, right, that's going to be this reverse. But because the numbers have those same properties, just like I was describing earlier, your textbooks tend to just show to the right of the curve. But they are completely symmetrical. Again, that's part of the beauty. So you can swap them one to the other. Okay, so now let's take the same example from earlier, and I'm going to convert a score of 675. So my mean, again, this was critical writing, was 475, standard deviation of 109. So this ends up giving me 200 divided by 109. It's a z-score of 1.83. So what I would do is I would look up 1.83 in the appendix, and I would find the corresponding area, which ends up being 0.466. I will show it to you in just a second. I just want to talk it through here. So you can then translate this portion of the percentage as 46.64% of the area under the curve. That includes between the mean and z, okay? So now let's actually look at it. So if I get this number, wait, what was it? 1.83, I would look at z, and I scroll all the way down until I get to 1.83. That is my z-score, right? Already, the fact that it's 1.83 tells me 2 things. It's over the mean, because it's a positive number, and in fact, it's almost 2 standard deviation above the mean. It's 1.83, so we're getting close to 2 standard deviation below, above the mean, I should say. So if I'm trying to find the percentage of the mean to z, for 1.83, that's 46.64, okay? So now, if I wanted to try to make sense of that, again, here's what it would look like. My mean is at 0 for a z-score. The z-score for this particular one, 675, is 1.83. So I know that this area is 46.64%. Now, if I'm getting that score on writing and I want to know, okay, well, what does that mean? Is my score better than X number than the mean? What I could do is I could also add this section, which we said is worth how much?
50%.
50%, right? This is 50% of the population is below the mean. So if I do 50% plus 46.64, that brings me to 96.64. So if I flip this into a percentile, all of a sudden I'm like, whoa, my score was at the 96th percentile. That gives so much more data, right? Than if just giving a score of 675. I wouldn't know what to do with that. Questions about how we manipulated all of this?
I'm good on this part, I think, but on if you could go back a slide, what's
Yep.
the other number? The percent in trail. Or
In tail.
Yeah. Oh,
Yep.
tail. Never
Tail.
mind.
Yep.
Yeah.
So this is reversing
Yeah.
it. And no, this is a great point. So this goes back to what Jenna was asking earlier about what if it's the flip side. So here I know that from the score where I'm at, right, this 1.83, here we are, the section that is from this point and beyond is only 3.36. So another way for me to get to my part where I just mentioned it's 96% is I could do 100 minus 3.36, and I would find out that that score falls at 96%.
Awesome.
Does that make sense?
Yep.
Okay. Again, that's the beauty of Z-scores. They're just interchangeable, right? Like you can make it above, you can make it below, because it's a symmetrical curve.
It is
Okay.
nice.
What's that?
I said it is nice.
Yeah. Okay. All right. Here's another example. Now, let's say writing is maybe not your strong suit. Nothing wrong with that, right? You got a score of 305. So now I would need to do the exact same calculation. So I take my score, 305, minus the mean, which I know to be 475, divided by the standard deviation, which is 109, which gives me a z-score of negative 1.56. Okay. Now I can plug that into my graph because again, a z-score, the mean is 0. That would be the 475 score. And then the z-score as received here is negative 0.1 or negative 1.56. Here's the 305. Okay, so I would go back into my chart and figure this out. So let's go back into, what is the 1.56? Here it is. 1.56 is right here. Now, whether it's negative or positive does not matter because the area under the curve is never going to be negative, right? So 1.56 and the mean, the percentage of mean to z is 44.06. So let's go back again to where we were. Here it is, 44.06% falls in this range.
Can I get a quick reminder on how we got the standard deviation from this?
Excellent question. Okay, so don't get car sick here, people. I'm gonna switch slides real fast. Bloop, 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 bloop. I went too far. There it is. No, I didn't go far enough. Sorry. Here, it was given to us.
Okay, so it'll be, that information will just be there.
Yes.
Okay.
Now, what I have done on exams before is first I have you figure, I give you a sample, like a specific sample. I have you figure out the mean, mode, median. Then I have you figure out the standard deviation. And then I have you figure out z-scores.
Okay.
Mixed bag with that because people are like, what if I make a mistake at the beginning? Then it's going to trickle down. And that's okay. As long as you're utilizing the right formulas, plugging in the right number, like the correct numbers you're pulling from, you'll still get points. So I usually do it a little bit of both ways. So you may be given to it as a provided as far as information, or you may be asked to calculate it.
Okay, thank you.
Okay, all right, I'm gonna go back and try to figure out which slide we're on here. Sorry. Is it thundering by you guys too, by the way?
Yep.
It is huge thunder. That's what was that?
It's also hailing.
It
like-
is?
Yeah, I don't know if it still is, but like I left work at 2 and it was hailing out.
It is not raining here. I'm just in Ada. I'm not that far, but let me know if you, well, I guess I'll know if you lose power if all of a sudden I'm teaching to no one. All right, we are going to go for another, let's see how, another like, let's do another 5 minutes and then we'll take a break because I got to reheat that tea. So I'm going to do it now.
Perfect.
Okay, So that's how we go through the calculations, figuring out the area under the curve. Now, part of what we were discussing earlier is you can also find the score above, right? So, oh, that is an error in your text. That's right. 2 years ago, I was like, what is this? This is not right. So you can find the area under the tails, right? If you get a specific score, it might be meaningful to get the area between the mean and it, but sometimes it's far more meaningful to talk about the area below, right? So this person scored at the 17th percentile, for instance, or 17% of people scored lower than they did. Or flipping it on its head, right? We could talk about how 83% of people scored better than this individual, okay? It allows us to speak about data in a more meaningful way. Similarly, oh my goodness. Did you guys all hear that?
Yeah.
That was really loud. Okay, all right, it's fine, we're good, it's just thunder, it's not a big deal. Okay. Similarly, if I scored 750, I'm like a whiz at writing, and I scored the z-score is 2.52. Now you're going 2.5 standard deviation above the means. Again, this should be 0.59%. It's a very, very small portion. So in fact, you scored in the like 99.4 percentile. Only 0.5% of folks scored better than you. All right, my dog is hiding now underneath my desk, so I apologize if she barks, if it starts thundering again. Okay. So now the beauty again of z-scores is we can ask almost any question of it and just manipulate the numbers to, and I don't say manipulate the numbers like fake it out, but like change the order of the formula to get the answer that you want. So if we want to find the score that corresponds with the top 10% of SAT test takers, you would figure out what the 10% in the tail corresponds to in a z-score, and you would then convert it to a raw score, okay? So it's taking the same formula we've been using, just changing it around so that we can solve for X. In this case, what is the score where at that score, you're at the top 10%. So that score and higher represents the top 10% of SAT test takers. Okay, so here's what it would look like. We would figure out this 10% in the tail, which is a z-score of 1.28, right? And then from there on, you would do 1.28 times your 109 standard deviation plus 475 for the mean, right? Which would give you a score of 615. Okay?
So was this standard deviation there? Was that from?
That's all still using that same example I was showing you guys earlier where we were given the standard deviation and the mean for the critical writing, critical reading, and math.
Okay.
Yeah, so that will be provided. Okay, questions?
All good.
Okay, so we could do the same thing if I was asking about the lowest 5%. You're like, I don't know, maybe you're like, how often does this happen? What's the lowest 5%? What is that score? You want to be careful again when you're going to do that calculation because of the mathematics of it. So once you get to that 5%, right, the lowest 5%, that would be 1.65. Now, again, your text will show it to you on this side, right? So find the 5%. Now you just need to flip it over so it's negative 1.65. And just think it through, right? If that ends up being your z-score, you plug this in. So negative 1.65 times your standard deviation, which is 109, plus your mean of 475, which gives you a score of 295. This is something I see with students all the time, where you plug in the numbers and you forget this negative piece right here with your z-score, and all of a sudden you end up with a score that's above the mean. Now you've got to look back at the question and go, what was it asking me? If it's asking me for the bottom 5%, I'm a visual learner, so I like to draw it out and do something exactly like what I did in this lecture. So you can see like it's supposed to be here. So if for some reason your number here was 530, that should give you pause, right? Like, wait, how can the raw score be 530 if my mean score is 475, right? That's illogical. this number needs to be smaller by virtue of the fact that it's left of the mean or it is below the mean. So set yourself up for success. Make sure that you do it visually too, so you can test out your scores and see what those look like. Does that make sense, everyone?
Yep.
Okay. Okay. All right. Let's take, let's come back at 3. How does that sound? We take a quick 10-minute break, come back at 3. We'll run through a few more examples and go from there. Sound good?
Yep.
Okay. See you guys in a few.